Hi everyone, this is Mrs. J, and today we're going to talk about set theory and probability. So first we're going to talk about some notation that we're going to be using throughout this unit. So first, it's important to know what a set is. So a set is simply a collection of distinct objects, and it's often shown with braces. So braces like this, and this would be the set. So this set has the numbers 1, 2, and 3. So an element is each object in the set. So 1 is one of the elements, 2 is an element, 3 is an element. An empty set, as you can guess, is just a set that is empty. There are no elements in it. So it can be denoted by this null symbol or just simply braces with nothing inside of them. And then a universal set is a set of all elements that are under consideration that is denoted by the capital U. So we're going to talk about how to write some different sets. We're going to practice writing some different sets. So let's say that set A is all of the prime numbers that are less than 10. So we start by saying A equals, and then we'll set up our braces like this. And we're simply just going to list all of the prime numbers that are less than 10. So 2, 3, 5, and 7. And then to denote how many numbers or how many elements are in this set, we would just say n of A, so the number of elements in set A equals 4. So let's say that set B is even whole numbers that are less than 10. So again, we're going to set up our braces, and we'll say B equals, and we just list them out. So 2, 4, 6, and 8. So again, the number of elements in set B is also 4. And let's say set C is all whole numbers that are less than 10 and multiples of 4. So let's set up set C with our braces. So that would just simply be 4 and 8. And the number of elements in set C is 2. And then lastly, our universal set would just be all natural numbers or all whole numbers that are less than 10. So our universal set would just be 1, 2, 3, 4, 5, 6, 7, 8, and 9. And the number of elements in our universal set is 9. So again, this is just for us to practice describing different sets. And we're actually going to use these sets in the next example, so make sure you have these written down as we go on to the next slide. All right, so now we're going to talk about the relationship among sets. And we're going to use those same sets that we did in the previous slide. So again, make sure you can reference those as we go through these. So we're going to start with this idea of a subset. So a set, so for example, set C is a subset of set B if every element of C is part of B. And we denote a subset like this with this kind of sideways U shape. So this means C is a subset of B. So in terms of a Venn diagram, it would mean that everything that's in set C is also in set B. However, it does not go the other way. There may be some elements that are in set B that are not in set C. So C is a subset of B. So if we were drawing that with our numbers from the previous example, we know that there are two numbers that are in set C. Well, both of the numbers in set C are also in set B. 4 and 8 are the only two numbers in set C, and they are also part of set B. But there were other numbers in set B that are included, so 2 and 6. So again, 2 and 6 are also part of B, but they are not part of C. So our subset is this area right here. But it's a subset of B. And then you could see that we also, our broader box is our universal set. So there we would list all of the other values that are not in B. So that would be 1, 3, 5, 7, and 9. Okay, let's talk about this next concept, which is the intersection of sets. So the intersection of sets, A and B, would be the elements that are in both A and B. So an intersection are the elements that work for both sets. And we denote it with kind of this upside down U shape. So in terms of a Venn diagram, you could see here's set A, here's set B. The intersection would be the ones that overlap that are in both. So if we look at our previous slide, those numbers and those sets, there's only one element that is both in set A and set B, and that is the number 2. So this is our intersection right here, the shaded part here. But there are some elements that are there are other elements in part A, so 3, 5, and 7. And there are other elements in set B, which would be 4, 6, and 8. And then within our universal set, there are 2 elements that are in neither A or B, so we'll include them on the outside, 1 and 9. Okay, let's look at the next concept, which is a union. So the union of 2 sets is all of the elements that are in either of the sets. So the union of sets A and B would be elements that are in A or B. So it's everything included. So it'd be the ones that are just in A, the ones that are just in B, and the ones in the intersection. And we denote a union with this U shape in the middle. Our Venn diagram, or our own with the numbers, will look very similar to the one above, except our shaded area would be all of it. So all of these elements are part of the union of A and B. So it's everything. Again, it does not need to work for both. It's just one or the other, or both. And then there are still two elements that are not part of A or B, so we'll list those on the outside. And the last concept is the complement of a set. So the complement of set A is the elements that are in the universal set but are not in set A. So the complement is the things that are not in that set. So we can denote this in 2 different ways. You might see something like this where it's like A with a C up where the exponent would be, or sometimes you see kind of the squiggle line with the A. I think this first one's a little bit more common, but this means the complement of A. So in terms of our Venn diagram, you can see the shaded part that's on the outside would represent the complement of A. So it's all of the parts that are in the universal set but not part of set A. So our complement here, so we know the numbers in set A are 2, 3, 5, and 7. So the numbers that are not would be, or the elements that are not, are 1, 4, 6, 8, and 9. And then we can kind of shade that area if it helps to show that the stuff not in part A would be the complement of A. So like this. So those are the 4 main relationships among sets that we will be working with. Okay, so now that we know how to use set notation and describe the relationship between sets, we're going to start talking about theoretical probabilities. So probability is simply a measure of how likely an event is to occur. And a probability will always be, the probability of something occurring will always be some value between 0 and 1, and it could include 0 or 1. So if an event is impossible, the probability is 0, and if an event is certain to happen, the probability is 1, and then all other probabilities would be somewhere in between. So a probability experiment is simply an activity that's involving chance. And a trial would be each repetition of that experiment. So we call an outcome each possible result of the experiment. Okay, and an event is simply a set of outcomes. So it's very common for us to find the probability of some event happening, and we know that, again, an event would include a set of outcomes because things don't usually just happen in one way. They can sometimes, but sometimes there's multiple ways that something can happen. So it'd be the set of all those outcomes. And then a sample space would be the set of all possible outcomes of our probability experiment. So when all outcomes are equally as likely to occur, we can find what's called the theoretical probability of an event. So we would denote that with P of A. So this is the probability of event A happening, which would be the number of outcomes in each event. So the number of ways that event A could happen, divided by the total number of outcomes in the sample space, which we would call N of S. So sometimes we see this written as kind of the favorable outcomes over the total outcomes. But again, it's just the number of outcomes in event A over the total number of outcomes in the sample space. All right, let's give this one a try together. So here we have the experiment of rolling a dice. So we know when we roll a dice, a dice has 6 sides, so it has 6 numbers. So it looks like event A, if you look at the numbers in event A must be rolling a prime number, And event B, if you look at the numbers included in event B, would be rolling an even number. And then you could see that 2 is an intersection of sets A and B because 2 is both prime and even. And then if you look at our universal set or our sample space, it will also include 1, which is neither prime nor even, but it's still a possible outcome, so it's part of our sample space. So we're going to calculate a few different probabilities. So let's start with the probability of event A happening. So to find the probability of event A, that probability would be the number of outcomes in event A divided by the total number of outcomes in our sample space. So the number of outcomes in event A would be 3. And the total number of outcomes you can count, or we know that a dice has 6 sides, so it would be 6. So the probability of rolling a prime number would be 1/2, 1/2. Okay, now let's find the probability of the intersection of A and B. So we're going to start with the number of outcomes in the intersection of A and B, and then we'll divide it again by the total number of outcomes, which will be the same as the first part. So there's only one outcome in this intersection. So there's one possible outcome there, 6 total. So our probability of rolling a prime and an even number is 1/6. Okay, now let's find the probability of the union. So A or B, so the probability of rolling an even number or a prime number. So here we want to find the number of outcomes within the union, and then we'll divide it by the total number of outcomes. So we can see that there's 5 outcomes within the union. Again, there's 6 possible outcomes in the sample space, so our probability is 5/6. And then the last thing we're going to find is the probability of the complement of A. So remember, that's the chance of A not happening. That's the complement. So we're going to find the number of outcomes that are not in set A, and we'll divide it by our total number of outcomes. So you can see here's set A, so there's actually 3 outcomes that are not part of set A. Total is 6, so our probability is 1/2. All right, let's try another one together. So here we are grocery shopping, and our grocery basket contains 1 bag of each of the following: a bag of oranges, green apples, green grapes, broccoli, white cauliflower, carrots, and spinach. So there's 1, 2, 3, 4, 5, 6, 7 things that are in our basket. So we are pulling items out of our basket to place on a conveyor belt for checkout. So event A, we're calling is picking a bag of vegetables first, and event B is picking a bag containing green foods first. So we're going to be finding a few different probabilities. So first, let's find the probability of event A happening. So that would be the number of outcomes in event A over the total number of outcomes. Well, we know the total number of outcomes is 7 because there's 7 bags to pick from. Again, event A is picking vegetables first. So if you count how many of these are vegetables, well, we have broccoli, cauliflower, carrots, and spinach. So that would be 4 outcomes. So the probability of event A happening is 4/7. All right, now let's see if we can find the probability of the union of event A and B. Remember, event B is picking a green food. So maybe let's list out all of the possible outcomes. That might make it easier for us. So we're going to list out any outcomes that are either vegetables or green. Does not need to be both. So we have the green apples. We have the green, I'll abbreviate, green grapes. We have the broccoli. We have the cauliflower. We have the carrots. And we have the spinach. And then that's going to be over 7. So if you count how many outcomes that is, there's 1, 2, 3, 4, 5, 6. So it's going to be a probability of 6/7. But remember, that was a union, so it's one or the other. It doesn't need to overlap. But this next one, part C, we're finding the probability of the intersection of A and B. So the outcomes need to be both vegetables and green. So maybe we can list this out again. So which things are vegetables and green? So we have broccoli, white cauliflower wouldn't work, carrots won't work. Oh, spinach works. Spinach is a vegetable and it's green. And then there's 7 possible outcomes. So our probability of the intersection of A and B is 2 out of 7. And then last, let's find the probability of the complement of A. So if event A is picking a bag of vegetables, the complement of A would be picking a bag that is not a vegetable. So that would include the oranges, the apples, the grapes, and the rest are vegetables. So that gives us a probability of 3 out of 7. So 3 out of the 7 things are not vegetables. Okay, so I have one for you to try on your own, so please pause the video and give it a shot. All right, so go ahead and check your work here. So for each of these, I listed out what the outcomes are of each event or each relationship of events. So in event A, it's just the numbers 1 through 10. Because here, if you're one of the first 10 students, then you're picking the numbers 1 through 10. So there's 10 outcomes in that event out of a 30 total, because you could pick anything from 1 to 30, so it's a probability of 1/3. Now the probability of A or B, so the union of A and B, so it'd be picking a 1 through 10 or a 12, 18, 24, or 30, which are other multiples of 6, which is event B. So that's 14 possible outcomes out of 30, so the probability is 7 out of 15. So the probability of events A and B happening, there's only one slip that is both the first 10 or a multiple of 6, and that's the number 6. So you have a 1 out of 30 chance. And here the probability of the complement of A happening. So the complement of A is not picking a 1 through 10, so that would mean picking an 11 through 30. So that's 20 possible outcomes out of 30, so your probability is 2 over 3. Okay, so now we're going to talk about ways that we can use the complement of event to help us maybe find a probability. So sometimes it's actually easier to calculate a probability of something happening by actually calculating the probability of something not happening. So we know that the probability of event A plus the probability of the complement of A must be 1. So if you think about it, right, if you add up the outcomes of A and not A, that will be all of the outcomes. So the probability of A happening plus the probability of A not happening would be all of the possible combinations. So it should equal 1. Now, going from that, we can kind of work with our complement in different ways. So we could say that the probability of A happening is 1 minus the probability of the complement of A. Or if you wanted to find the probability of the complement of A, it would simply be 1 minus the probability of A. Okay, so let's do another example together. So here you are rolling 2 dice, and we want to know what is the probability that you do not roll doubles. And we're going to use the complement to help us calculate this probability. So if event A is not rolling a double, the complement of A would be rolling a double. And if you kind of list out all of the possibilities of rolling 2 dice, here's all of your possible outcomes, you could see that it's a lot faster to count the number of times that you roll a double than to count all of the times that you don't roll a double. So here it's actually easier to use the complement. So the complement of A, there's 6 possible outcomes, and then you could see that there's 36 in our sample space. So we could say the probability of A would be 1 minus the probability of the complement of A. So the probability of A is 1 minus, well, there's 6 favorable outcomes here, and then there's 36 possible outcomes. So the probability of A would simply be 1 minus 1/6, which is 5/6. So you can see that it's just simply faster for us to work with the times that are not A than all of the times that are A. Okay, let's try another one together. So here, 1 bag of marbles contains 2 red, 1 yellow, 1 green, and 1 blue. And another bag contains 1 marble of each of the same 4 colors. So 1 marble of each bag is chosen at a time. We're going to use the complement to calculate the following probabilities. So let's just start by thinking about the outcomes that we have here. In that first bag, there are 5 marbles. There's a red, a yellow, a green, and a blue. And then in our second bag, there's just 4 marbles. There's a red, yellow, a green, and a blue. So you could see that if I make a chart like this, this would give me all of the possible outcomes. So we have 20 possible outcomes here. And we would just, like this box would be RR, RR, RY, RG, RB. So we could fill them in, or you can kind of just visualize where they are. So for this first question, they asked, what's the probability of selecting 2 different colors? So I would say we should just do 1 minus the probability of the complement, which is selecting 2 of the same color. So we can see that there's only going to be a few times when it's the same color. I'll highlight it in gray. So here and here, so those are our R's, and then there's this one, and this one. So there are just 5 times when it is the same color. So the probability of it being the same color would be 5 out of 20. So we just do 1 minus 1/4, so 3/4. So again, instead of counting all the times when it could be different colors, we could just count the number of times when it's the complement of that, which would be the same color, so because there's just fewer options to count. Now let's try this next part. So the probability of not selecting a yellow, well, to use the complement, we do 1 minus the probability of selecting a yellow. So I'll highlight those in yellow, all of the different times when we are selecting a yellow. So that would be everything here or everything here. So if we count up all of those boxes, it's 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 possible times when I could select a yellow out of 20. So it's 1 minus 2/5, so 3/5. So you can see here, it's just useful to use the complement because there are fewer times where you are selecting a yellow than when you're not selecting a yellow, so it's just a little bit faster of a process. Okay, so here I have one for you to try on your own, so go ahead and pause the video and give it a shot. Okay, so go ahead and check your work here. So you can see that the total number of outcomes is 25. And if event A is the sum being less than 12, that means the complement of A would be the sum being greater than or equal to 12. So you can see that those 6 cases are here. So 6 out of 25 would be the probability of the complement. So if you do 1 minus that, you get the probability of A, which is 19/25. Okay, that is all for today's video. Thank you so much for watching.